The next thing we're going to look at is Theorem 6.21, which discusses the existence of power series solutions. Let's suppose that x equals to x naught is an ordinary point of the differential equation. Then we can always find two linearly independent solutions in the form of a power series centered at x naught. That is, y equals to the sum from n equals 0 to infinity c sub n times x minus x naught to the n. A power series converges for at least on some interval defined by x minus x naught is less than r, where r is the distance from x sub 0 to the closest singular point. Okay. Notice that this isn't defined as the radius of convergence of the series, but it will converge at least for that distance. So potentially we will see certainly that the radius of convergence could be bigger than this, the distance from x naught to the nearest singular point, but at the very minimum it will converge over that interval. Let's take a look at an example. In example 4, they say find the minimum radius of convergence of a power series of x squared minus 2x plus 5 y double prime plus x y prime minus y equals to 0. And we're going to do it about the ordinary point x equals to 0 and about the ordinary point x equals to negative 1. So let's begin by first of all writing this differential equation in standard form. It's y double prime plus, we would divide everything by that quadratic polynomial divided by x squared minus 2x plus 5. That's going to be y prime minus 1 divided by x squared minus 2x plus 5 times y, and that's going to be equal to 0. Let's find the singular points for this differential equation. They're found by solving wherever the denominator is equal to 0. So solving this will give us our singular points. It won't factor, so we're going to need to use the quadratic formula. It's going to be the negative of negative 2 plus or minus the square root of negative 2 squared minus 4 times a times c, all divided by 2 times a. This is going to give us 2 plus or minus, we're going to get a negative 16 under the radical, so that should be plus or minus 4i over 2, and this is going to give us 1 plus or minus 2i. So the singular points of this differential equation are x equals 1 plus or minus 2i. Let's now go ahead and find the minimum radius of convergence of the power series. They said that it's at least the distance from our ordinary point to the complex numbers. Here we're kind of fortunate that we don't have to compute both distances. You can see very quickly if you graph this in the complex plane, here would be our ordinary point in part A. We have the ordinary point x equals to 0. And then these singular points would be at 1 plus 2i and 1 minus 2i. So you can see very quickly via symmetry that those two distances are going to be the same. So maybe I'll find the distance between x equals to 0 and x equals to, let's say, 1 plus 2i. An easy way to do this is if you associate to the complex number the ordered pair in the plane A comma B, then it's simply just using the distance formula in the plane. This is the square root of x2 minus x1 squared plus y2 minus y1 squared, where x is the real part of the complex number and y would be the imaginary part. So for 0, it's going to be 0 and 0, and for x it's 1 and 2. So it's going to be 1 minus 0 squared plus 2 minus 0 squared, and that's going to give us the square root of 5. So the square root of 5, this is the distance from 0 to either one of our two ordinary points. And therefore, we know that this power series will converge within a distance of radical 5, at least. So we're guaranteed that the power series solution, we're not actually going to solve it for it, but we would know that it would at least converge. These converges for x less than square root of 5. Let's now do the same thing. Let's find the minimum radius of convergence for our power series solution about the ordinary point x equals to -1. Again, via symmetry, here's -1 on the real axis, and this is where either one of our two complex points would be. The distance between the two is going to be the same, so we just need to compute the distance from x equals to -1 to one of the complex numbers. So maybe I'll compute the distance between x equals -1, and let's use the same one. Let's say x equals 1 plus 2i. The distance between those two numbers is going to be 1 minus a -1 squared plus 2 minus 0 squared. This is going to be 2 squared is 4. 2 squared is again 4. So we get the square root of 8, which you could break down to 2 radical 2. So our other power series would at least converge the distance from x to the ordinary point -1, that's x minus -1, will at least converge as long as the distance is less than 2 square roots of 2. So that's one of the things that we know in terms of at least getting a minimum radius of convergence for these. It can be shown if we were to actually go through and find the power series solution for this differential equation, that about one of the ordinary points you would actually have an infinite radius of convergence, but at the very minimum we know we do get a minimum radius of convergence from this last theorem. Again, and how do we find that minimum radius of convergence? Again, it's found by taking the distance between the ordinary point where you want to center your series and the nearest singular point. Let's take a look at one. In example 5, let's solve y double prime minus xy equals to 0. And for this one, there's no singular points, first of all. It's already in standard form. The y prime term is missing, so there's no p of x, so p of x is 0. That's a constant polynomial. And the coefficient for q is x, that's a polynomial. And we know that those functions are analytic everywhere. Therefore, every point would be an ordinary point of this differential equation. Let's go ahead and assume a power series solution. So let's assume, and let's let y be equal to the sum from n equals 0 to infinity of Cn x to the n. We need the second derivative to plug this in. So let's take the first derivative. That's going to be the sum now from n equals 1 to infinity of n Cn x to the n minus 1. To take the second derivative, this is now going to be the sum from n equals to 2 of infinity. Again, bring the power down. We have n times n minus 1 Cn x to the n minus 2. We can now take those series and plug them into our differential equation. So we're going to get y double prime, which is the sum from n equals 2 to infinity of n times n minus 1 Cn times x to the n minus 2 minus x times the sum from n equals 1 to infinity of n cn x to the n minus 1. And this whole thing is supposed to be equal to 0. So we have everything plugged in. One of the things that we can kind of do here, if we would like to, is we have this x. Excuse me, I plugged the wrong one in. This is not y prime. This is y. My apologies. This is the sum that should be multiplying to x. So sum from n equals 0 to infinity of c and x to the n. And then let's bring this x into the inside. We can combine those terms, multiply them by like bases. That's going to add those exponents. So this is the sum from n equals 2 to infinity of n times n minus 1 cn x to the n minus 2 minus the sum from n equals 0 to infinity of cn, and now this becomes x to the n plus 1, and this whole thing is supposed to be equal to 0. Okay. The very next step is we want to kind of combine these two. So we want to combine these two series into one series. Let's investigate for which power of x does each one start. Well, notice that when n equals to 2, this is going to start at x to the 2 minus 2, which is x to the 0, or a constant term. Over here, when n is equal to 0, where this series starts, it's going to begin with an x to the 0 plus 1, which is an x to the first term. In order to get them to start at the same term, the same power of x that is, let's break off and write the first term of this series, which would be the constant term. When n equals to 2, if we plug that in, we're going to get 2 times 1 times c2, which is 2c2. X to the 0 we know is 1. So that's the first term by just plugging n equals to 2 in. Plus, then we can write the remaining terms as the sum now from n equals to 3 to infinity of n minus 1 cn x to the n minus 2 minus the sum from n equals 0 to infinity of cn x to the n plus 1, which is equal to 0. Okay. Now that they both start at exactly the same place, we can go ahead and re-index. So let's go ahead and re-index these. For the first sum, we're going to let k be equal to the exponent, n minus 2, which coincidentally would tell us that k plus 2 equals to n. For this one, we're going to let k be n plus 1, which would tell us that k minus 1 would be equal to n. Under that change of index, we get that this is equal to 2c2 plus the sum from now k equals, notice that if n is 3, then k is going to be 3 minus 2, which is 1, to infinity of everywhere I see an n, we can put k plus 2. So this is going to be k plus 2 times k plus 2 minus 1 ends up being k plus 1, c to the k plus 2, and now this is x to the k, minus the sum from k equals over here. When n is 0, then k is going to be 0 plus 1, which is 1, to infinity of c to the k minus 1, x to the, this is k. This whole thing is equal to 0. And now what we can go ahead and do is we can combine the two sums. So we have 2c2 plus the sum from k equals 1 to infinity of the following: k plus 2 times k plus 1, c of k plus 2 minus c of k minus 1 times x to the k, and now this whole thing is going to be equal to 0. Okay, and so now we've combined all of our terms into one series, and we know that the series is set equal to 0, which means that now all of these coefficients have to be equal to 0. In particular, if you look at the left-hand side, that's going to tell us that 2c2, which is the constant term, would have to be equal to the constant term coefficient on the right-hand side, which is 0, which tells us that c2 is going to be equal to 0. But then, in addition, the coefficients of our x terms, this k plus 2 times k plus 1, ck plus 2 minus ck minus 1, is also going to have to be equal to 0. We're going to solve this recurrence relation for the largest index of summation. K plus 2 is bigger than k plus 1. So we're going to solve it for ck plus 2. You would add the ck minus 1 to both sides, divide by this factor, and what we get is that ck minus 1 divided by k plus 2 times k plus 1 is equal to ck plus 2. And now from here, let's try and plug in a couple values for the index k to see what we kind of end up with. So we already know that c2 is equal to 0. And now for our ck plus 2, which is ck minus 1 divided by k plus 2, k plus 1. Now notice if we try to plug k equals to 0 into this, we would get a 0 minus 1, which is negative 1. But our series doesn't start until the constant term, which would be the one that has a c1 with it. So anyway, even if you try to plug k equals to 0 into this, we already have the value of c2. We know c2 is equal to 0. So the first value that makes sense would be to plug in k equals to 1. This would give us the value of 2 plus 1 is 3, which is going to be equal to c0 divided by 0 plus 2 times 0 plus 1, which is 1/2 c0. Excuse me, no, plug the k equals to 1 in. Duh. It's going to be c0 divided by 1 plus 2 times 1 plus 1. There we are. So this should be equal to, it's going to be a 1/6 c0. So c3 is equal to 1/6 c0. And where that 1/6 came from, maybe I'll show this extra step, because it's going to be enlightening later. This was, what, 3 times 2, which is where that came from. Now let's go ahead and plug in k equals to 2. If k equals to 2, then we get c4, 2 plus 2 is 4, is going to be equal to c of 2 minus 1 is 1. So we get c1 divided by 2 plus 2 times 2 plus 1. So this is c1 over 4 times 3, which is simply 1/12 c1. When k equals to 3, that's going to give us c5. This is going to be equal to 3 minus 1 is 2, all over 3 plus 2 times 3 plus 1, which is C2 divided by 5 times 4, which is going to be 1 over 20 C2. However, we know what C2 is equal to. Remember, C2 is equal to 0. So this whole coefficient is going to be 0, so C5 is equal to 0. Let's work out a few more to see if maybe we can notice a pattern. When k is 4, this is going to give us C6 equals, this is going to be C3 divided by 4 plus 2 is 6, 4 plus 1 is 5, so we're going to get a 1 over 30 C3. But if you look back, we know what C3 is equal to. C3 is equal to 1/6 C0. So it's going to be 1 over 30 times 1/6 C0, which is going to give us 180 C0. So C6 is going to be 180 C0. Do a few more. If k equals to 5, then we get C7. It's equal to, this is going to be C4 divided by 4 plus 2, excuse me, 5 plus 2. Okay, it's 5 right now. 5 plus 2 times 5 plus 1, which is C4 divided by 7 times 6, which is 1 over 42 C4. But we know what C4 is equal to. C4 is equal to 1 over 12th C1. So this is 1 over 42 times 1 over 12 C1. Which I'm going to kind of write this maybe in factored form, perhaps would be the way to kind of write this. You know, if we broke this apart, it's going to help us to see the pattern here in a minute. The 42 was 6 times 7, which is 2 times 3 times 7. And the 1 over 12 here was what? I'll write it like this. Actually write it like this. So we'll do a 3. I don't need to break it to primes. Let's call it 3 times 4 times 6 times 7 C1. Similarly, if we go back to C6, a convenient way to write this was 2 times 3 times 5 times 6 C0. This one is 0. Our C4, which I have over here, C4 is going to be C1 over 3 times 4. And now let's kind of write out the terms that we get. Notice that one of the things that's going to quickly be prevalent here is that if we were to go for, like, let's say C8, so when k is equal to 6, we would have a 6 minus 1, which would be 5, and that term would also be 0 because C5 was 0. So I'm running out of room. Let me just try and keep what I can and get rid of the rest. In general, you need to kind of do about as many of these as what it takes to kind of spot a pattern. So again, our power series solution should be able to form C0 plus C1x plus C2x squared plus C cubed x cubed plus dot dot dot. We don't know the value of C0, it's arbitrary. We don't know the value of C1, it's arbitrary. We know that C2 is 0. We know that C3 is 1/6 C0, which I'm going to write like this. I'm going to go back to the factored form of it. It was 2 times 3 And that's going to be x cubed plus our C4, which is this coefficient right here. So it's going to be plus, where was it? Sorry. C4, where am I? You can write this as 1 over actually we'll call it C1 over 3 times 4 x to the 4th plus our next one was C5, but C5 was 0, so we get a 0 x to the 5th. Our C6 term is this thing right here. It's 1 over 2 times 3 times 5 times 6 C0 times x to the 6th plus dot 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 dot. So this is what we get for our power series solution. And one of the things that we kind of realized, remember this was a second order linear differential equation. So usually the solutions are of the form y equals then we call it C0 times some function of y1 of x plus C1 times some function of y2 of x, where y1 and y2 would be our old school linearly independent solutions to that second order linear differential equation. And so when you see that previous theorem where it talked about there being at least 2 power series solutions, this is kind of like where they're coming from. One represents the one function y1, the other one would represent the linearly independent solution y2. If we wanted to kind of write them in more depth, we can break them apart. It's the terms that contain the C0 would all form one series, and the ones that have the coefficient C1 of them would be the other ones. So the y1 of x, if you want to break this apart, so any of the ones that had the C0 with it, so this would be like our 1, and let me actually factor it out, I think it might make more sense. If you factor out the C0 from the like terms here, you would have 1 plus this thing, which would be 1 over 2 times 3 x cubed. And then if we kept on going, I don't have the next one written down. Yeah, I do. C0 right here. Plus 1 over 2 times 3 times 5 times 6 x to the 6th, etc. We could actually write this in closed form if we wanted to. This is C0 times the sum. Actually break out the 1 first, because the 1's kind of hard to work into it. We have 1 plus, and now what we see is we're always going to have powers of x that are multiples of 3. So it's going to go from k equals to 1 to infinity of x to the 3k, and then this product that we're seeing in the denominator, it goes 2, 3, 5, 6, 8, 9, which is multiplying, 2 times 3. Then we get 5 times 6, so it's kind of like multiplying by pairs, skipping over the things that have like a 4 in it. And then it would keep multiplying until we get to 3k minus 1 to 3k. And then that second solution would be the ones that have the C1 in it. If I factor anything out that has C1 in it, we get x plus this one here, which would be 1 over 3 times 4 x to the 4th. And then the next term, it's not showing up, but then that would have been our so we have the x to the 4th, it would have been x to the 7th. Again, it also goes up by 3's. And it would have been 3 times 4 times 6 times 7, x to the 7th. We actually did show that when we were computing a few of these. So we have the C1, and if I break off the first term of x, we can write the remainder of it as the sum from k equals to 1 to infinity of, now here these are all one more than a power of 3, so it's x to the, excuse me, one more than a multiple of 3, so they're all of the form exponents 3k plus 1, where here actually k should start at no, that's right, yeah, if I break the x off, it's going to start at 4, so k should start at 1, and if we look at kind of like the product that we have in the denominator here, it goes 3, 4, 3 times 4, then it skips 5 times 6 times 7, and then it would skip 8, and then the next one would have like a 9 times 10, so we get 3 times 4 times 6 times 7, and it's always multiplying numbers of the form 3k up until we get to 3k plus 1, right? The last factor matches the exponent that we have there.